Thanks for the invitation to talk at this great event. I feel slightly outnumbered being British in this audience of fantastic friends. Oh, yes. Well, you're not really anymore, are you, Roger? Emma as well here, so we're okay. I guess I remember when I just finished my PhD. I did my PhD in the late 1990s, and Jeff King came and gave a talk in Oxford. So I guess that was him going into the lion's den in those days. And he brought a very big slab of French brie and really used this as an analogy. So I think, let's see, can I get this to work? No, I'll show you that. Yeah, so I guess I haven't actually got any brie, but I think a lot of the debate back in those days was, does the continents behave like this lovely, mature French cheese, which bizarrely was what the Brits thought, or more like this English cheddar, you know? So it was kind of like this. So and it did get somewhat heated in those days, but I guess what this talk is really is, well, how do the continents really deform? And I'm a data guy. I want to see how the ground actually moves. So before I go on, science is a team sport. Pretty much nothing that I'm showing I've done myself. So in particular, I want to thank Jin Fang and Greg Hausman. Jin's just finished his PhD in Leeds, and a lot of the work is his. But also there's a very large team of people who've been involved in the InSAR processing over the years. It's been a 10-year effort to kind of get to where we are with that data set. So we're entering this era of geodetic big data. This is continuous GNSS data processed by the Nevada Geodetic Lab, tens of thousands of sites. At the same time, we've got incredible InSAR data from systems like Sentinel-1. And Sentinel-1's in particular has been a game changer. It's a European satellite. It's acquiring data systematically over all the tectonic and volcanic areas. And that data is free and open for anyone to use for any purpose. So we've been able to do this mass processing. There's been groups in France doing this as well, exploiting this incredible resource that's measuring how the Earth deforms. I'm going to talk a little bit about the methodology before going on to talk about what it means, but the basics of what we do is we make interferograms from those radar images. We form networks. We then invert for average velocities in individual areas, and then we tile those together to give us a velocity field. So just going in a little bit more detail, we do those interferograms in 250 by 250 kilometer frames. The details are in this paper by Milan Lazecki. We've been doing this in basically a completely open way. I just had an email this morning saying we've now ticked over 2 million interferograms that have been processed by the system. They're all online, available for anyone to use for whatever purpose you want. So I encourage you to do that. So we make the interferograms, we make these networks. We've got 10 years of data now for a lot of the deforming continents. We then invert for the average velocities. We make various corrections for the troposphere, the ionosphere, earth tides, plate motions. We remove the earthquakes, if there are any earthquakes that are bigger than 6 that deform the frames. And it's a big data set. So just for Tibet alone, we've got something like 260 of these 250 by 250 kilometer frames, 52,000 satellite images, from which we formed about 200,000 interferograms. It's a lot of data. We then tile those together with GNSS and some leveling data, actually for the vertical, using an approach we published back in 2012. The idea here is that we essentially solve the 3D velocities of the nodes in a mesh of spherical triangles. Those are about 0.2 degrees spacing. And at the same time, we solve for reference frame adjustment parameters for each of the InSAR frames to try and tie it all together. That gives us these beautiful mosaics of interferograms. This is data as the satellite goes from north to south. You can see blue is motion towards the satellite, so you can see that eastward movement of Tibet there. If we look at the data acquired as the satellite goes from south to north, it's looking to the side again, so we see the opposite color because Tibet in this case is moving away from the satellite. We then combine those on a pixel by pixel basis, the ascending data and the descending data. You'll note we've only got 2 observations at InSAR resolution, so we can only really get 2D. We get around that by using the north-south from essentially the GNSS data. So that's really an interpolated velocity field. But we can do a pixel-wise inversion for east-west velocity and vertical velocity. The vertical velocities, there's lots of stuff going on in here. Most of it, I think, is non-tectonic. There are some tectonic signals in there, but there's signals from permafrost, from water extraction, from mining, a number of different things in that vertical field. I'm going to concentrate, though, on the horizontal, which really shows that, I should say that, this is matching to the data. We fit that to the vertical to about 2.4 millimeters. The horizontal is where I really want to concentrate on, and this is hot off the press. This new iteration came out just last week with the latest update on our data. Really beautiful velocity field. Again, it matches the GPS very well. That's not really a surprise because we've tied it to the GPS. But you can see this information in there. How do I get a laser? Yeah, so if you look at places where there aren't GPS, we're providing extra information, particularly this gap here, for example. You can see some of these gradients around the faults. So it's not just interpolating the GPS, we're adding high resolution information in here. I think profiles of the deformation are quite instructive. So the three on the right are those three north-south profiles. What you can see, I think, and this is going to be the theme of the talk, is that neither brie nor cheddar are appropriate cheeses for Tibet. It's probably, if I take a positive spin on the results, it's both. So both are correct. If we take a negative spin, then they're both are wrong. But we'll see. So what you can see, if we look, for example, at profile B, yes, there's a step here across the Altyn-Tag fault, but there's this very smooth, long wavelength deformation signal. The same is true in these other profiles where they cross some of the big strike-slip faults, the Kunlun fault, the Altyn-Tag fault, the Zhangzhou fault, etc. We get steps in those profiles. But if we look at this east-west velocity profile that doesn't go over any of those big strike-slip faults, it's pretty smooth. It's hard to argue that there are giant steps in that profile. It's actually more useful, I think, to look at the strains, and the strains can actually tell you what's deforming. So from this, we can see the key features. So on the left here, we've got the maximum shear strain rates. On the right, the horizontal dilatation rates. These are coming from where we've just got the InSAR data. We can add in data from where we've got just GPS. So this is noisier, and to give us a more complete picture. And I think this really shows the key features of how Tibet is deforming. So we are seeing focused strain around these big strike-slip faults. We've heard a lot about those in this meeting already, and also around the Himalayas. We've got areas with relatively low strain. Again, we've heard about some of those already. I'd argue we've got an area of distributed strain here in the center. And I think it's worth reflecting. One of the things when you get geologists of my generation and junior, you always have this thing where you do something, you think you've discovered something, you look it up and you discover that actually Tapponnier or Mackenzie's done it before, right? So, and published it in the 1970s. But it's really remarkable, I think, in this map that we've seen a few times already, just how those key faults are identified back in the 70s based on satellite imagery. And really, those big faults are the ones that are active in the present day deformation field, with a few exceptions. The Karakoram fault doesn't particularly light up, for example. If we look at the dilatation field, we can see that that all the way really from the Himalayas all the way up to the Kunlun fault, we've got dilatation, positive dilatation. It's compressing north-south, but the extension is beating that dilatation. The extension is beating the compression. We've also got around the Himalayas, but also in this north area, this contraction. So we are building topography, and again, that's consistent with this idea of that growth in the plateau happening in that northern region. Another thing we see quite clearly is some evidence of long-lived deformation associated with previous earthquakes that happened, some of them quite a long time ago. Mani from 1997, for example. So I want to just go on a quick detour about earthquake cycle temporal deformation. So I'm going to just quickly go to the North Anatolian fault. We're going to look at strain accumulation across the entire North Anatolian fault. What you can see is we get these focused strain profiles pretty much consistently along the fault. This is work from Iqbal Hussain, published in 2018. What the nice thing he did was said, okay, we can look at any one location. We can say, how long ago was the earthquake in that one location? And then you can build up a graph like this, which is the strain rate as a function of time since the last earthquake. You can build up a story like this. These are derived from InSAR and GNSS. This was GNSS data acquired before the 1999 earthquakes. This was post-seismic data measured after the 1999 quakes. And essentially, you've got this post-seismic period that maybe lasts 20 years or so, but then the strain rate for the entire North Anatolian fault, at least, is pretty constant. So if that holds for all faults, then it suggests short-term strain. If we avoid those post-seismic intervals, it's pretty representative. It has some implications in terms of the strength of the lower crust, the viscosity of the lower crust. I haven't got time to explain, but essentially you need it to be quite a lot higher than some of the estimates from post-seismic deformation. So the key features, I think, of continental deformation, we've got focused strain around large fault systems, diffuse strain away from those major fault systems, spatial variability in that strain rate, so implying regional differences in strength. And we've got large earthquakes that seem to influence the deformation field for several decades. This was a quote that my old PhD supervisor, Philip England, used to like a lot, that all models are wrong, but some are useful. I used to think he'd come up with it, but actually it was George Box, an American statistician, who coined that phrase. I think in this context, I think different applications require different models. So if we're interested in the seismic hazard in a region, we want to answer questions like, what are the slip rates on faults? How much strain is accommodated away from those major faults? Then we might want to think about kinematic models. We don't really care about the forces or the rheology. We just want to know what's going on, how fast are the faults moving. If we're thinking about what controls the deformation of the continents, we're thinking about the rheology, how it varies in space, what's the role of faulting, then we're going to need to look at dynamic models. And I'm going to show you examples of both. We'll start with the kinematic approach. Block modeling is a common approach for geodesy. It's not one I particularly like, and I don't think it's particularly useful geologically. So what you do here is that you divide up a region like Tibet or Southeast Tibet in this case into blocks. Each of those has to follow the rules of plate tectonics. So it's pretty efficient to invert, particularly if you've got sparse GNSS data. I should stop waving my hands around so much. Yeah, it's nerves. So there's only 3 parameters per block, essentially. So it's a pretty efficient system. Although if you go to the extent of Richard Styron and have 264 blocks, you quickly build up your number of parameters. I think the reason I think it's problematic is that all the strain has to occur on those block boundaries. And these blocks each block has to be fully surrounded by faults, even if they don't exist. You can see here the block boundaries that Richard Styron defined here. The white ones are boundaries where there's no mapped fault. So the question is, do these match the data? We've now got really dense GNSS data, or is there a better approach we can use? I'm going to show some work from Jin Fang. We've got a poster on this that will be up later in the meeting, so we can have a more detailed discussion. Just focusing in on Southeast Tibet. Here, there's the Jiangsu fault. You can see here's the shear strain rate. Again, what you see is the same story as before. This, by the way, is the creeping section. So we get a very high strain rate there. But you see these 2 big faults here dominating that shear strain. If you look at the best fit shear strain using those blocks from Richard Styron, it doesn't quite look like this data. For example, here's a block boundary that basically, because you've got a boundary there in the model, you end up with predicting some strain there. It doesn't really exist in the real data.
Tim, can I ask a question?
Yeah.
Some strain not on fault, it's not sigmoid, it's off the fault. Some gets narrow and some gets wide. What's your interpretation of that? You said it's associated with faulting.
I think in the data or in the model. In the data I'll come on to. Yeah, there's definitely distributed strain as well. For sure. So you particularly see it in the dilatation. So here, if you look again in the block models, you have to put strain on the individual faults, but actually in the data, it's much more diffuse. So there's definitely diffuse deformation going on, in my view, as well as the focused deformation on the strike slip faults. So we've been taking a different approach. It's still a kinematic approach, but if you actually, this is work we've done with Kai Johnson, adapting a method that he's developed. Essentially what you can do is, rather than invert the velocities, if you invert the strains, you don't have to worry about the rotations anywhere. You just worry about the deformation associated with the faults. If you just put the mapped faults in, you can get about half the deformation that you can match in terms of the strains. You need to then also impose some kind of distributed source. So I'm not necessarily saying what's going on there, but an efficient way of modeling that is to have a set of distributed sources, and then you can match this data pretty well. And there's some more different approaches in the poster, so I encourage you to come and have a look at that. So we've got this idea that there is this bimodal behavior. Can we try and explain that with a dynamic model? So being Oxford educated, we've gone back to those viscous models, started with a thin viscous sheet approach. So here we've got a 2D depth averaged rheology, power law viscous rheology. There are buoyancy forces that arise from gravitational potential energy. So the topography is built into this, and those are important. The boundary conditions in this case, I'm not worried about where they're coming from. We're basically set those based in most cases on the known plate motions. And we have a relatively strong Indian indenter in this case. If we just, so I'm going to basically compare the predictions of these models to the data, just in terms of the east velocity component. Here's the prediction, here's the data. And in the top right, there's a misfit. So we start off with about just this pure, very, very simple model, uniform strength everywhere. You don't really do a very good job of fitting the data at all. If you include stronger regions, such as the Tarim, Sichuan, etc., you do a little bit better. If you make Tibet, well, if you make the high elevation regions weaker, you do better. We're starting to get this really, I mean, I think the really striking observation here is this strong gradient in eastward velocity, and the fact that it extends all the way from the arc up to the Kunlun fault. I think that's quite a challenging observation to reproduce in these models. If you put in a weak, further weakening in central Tibet, you can start to approach it, but it's not an entirely satisfactory fit. The misfit here is about 5 millimeters, not bad for a relatively simple model, but it's capturing some of the information there, but not everything. So an alternative approach is to put faults in the model, and we had a preview of that this morning. If you start straight away, you keep everything uniform apart from these stronger blocks, put some faults in. We're already doing better here than the viscous model without faults. The way we parameterize the faults is they're essentially discontinuities where there's a shear traction that's proportional to the difference in velocity across those faults with a constant of proportionality. Here, we can gradually make this better. So if you just compare it to the equivalent viscous model without faults, I think it's worth noting these faults make a big difference to the velocity field, right? Maybe this is not a surprise, but it's not just a localized difference. These are not just passive markers responding to that underlying velocity field. They're influencing the velocity field over distances that's something like approaching the length of those fault structures. So these are important in influencing the velocity field. If you make high elevations weaker, you do an even better fit. If you put that weak zone in central Tibet, you do even better. So we're now getting down to fitting the geodetic observations to about 3 millimeters with this model. So, okay, key lessons, right? I think cheese is too simple. The Earth isn't cheese. I think, but yeah, both of those views are wrong or both are right. I think there is distributed deformation. There is, I've done it again. There is faulting, right? This maybe the rest of the world has moved on and realized this a long time ago, I think, as well. But the data are good enough now to see processes on the scales that matter. Okay, we've got this bimodal behavior. So strain is focused around major fault systems, more continuous elsewhere. We need spatial variations in strength. Geological history matters. Major faults aren't passive markers, but influence the velocity field. For example, I think there's evidence, geological evidence of the mobilization of the Kunlun Fault in the mid-Miocene. And I think that's probably inextricably linked to the east-west extension that we see in Tibet. And I think that that's an area that's, I think, worth further thinking about. These faulted continuum models are one way of providing a relatively simple approach to testing hypotheses. Just a quick diversion to Scotland, where why do we have this bimodal behavior? We've been looking at a shear zone. This is a 1.8 billion year old shear zone in northwest Scotland. You can see here this dike that runs through this granulite facies wall rock into this shear zone, which is hydrated and has amphibolite facies. And you can see how as soon as you get into that amphibolite facies, it's much, much weaker. You can see that bending of that granulite of the dike within that. These rocks were basically a few kilometers below the seismogenic line. So I think this is the critical part of the crust that we need to be thinking about. This is work by Manon Carpenter. There's a preprint on Earth Archive. The model that she's come up with actually essentially is saying that as this shear zone evolves, it hydrates itself, so the water is brought in because of the faulting. That then enables, so there's sort of a positive feedback loop. And in particular, there's dissolution precipitation creep seems to be a really important mechanism within this particular location. So essentially, I think if fault geometries are stable, they modify their own rheology, they modify the temperature, the grain size, fluids, mineralogy, etc. So I think that's one explanation why these big strike slip faults appear to be different. Okay, I should say we're working on even bigger velocity field. This will be submitted hopefully this year. John Elliott is pushing this through. This is an early iteration of it. So questions, is Tibet just unusual? Is it fundamentally different? Do small faults matter? What's the contribution of low strain regions? How time dependent is deformation? We've essentially been trying to argue it's static, but I think as we get longer and longer time series, we'll see that that's not the case. How do we incorporate advances in metamorphic petrology into our understanding of models of continental deformation? How important is 3D deformation? Clearly, the Earth isn't 2D. 3D matters. What's the relationship between brittle faults and the underlying ductile behavior? Is it different for smaller faults than bigger faults? How can we combine all of this information, particularly the strain rate data that's fairly short term, with other data sets to improve seismic hazard models? So I think I've had my 20 minutes and I will end there. So thank you.